very honored to have Professor Calin Belta from Boston University. Calin is a distinguished professor at Boston University in a number of departments: mechanical engineering, electrical and computer engineering, and systems engineering. He's also the director of the BU Robotics Lab. His group works on the dynamics and control theory with a particular emphasis on several physical systems and formal methods and their applications to robotics and system biology. Calin has a number of awards, including the AFOSR Young Investigator Award, the NSF Career Award, and the 2017 IEEE Transactional Control Network System Distinguished Outstanding Paper Award. Calin is also an IEEE fellow, and a distinguished lecturer of the IEEE Control System Society. Calin, welcome, and
thank you.
I will give you the floor.
Thank you. Thank you for the invitation. It's great to be here. I think last time when I was here, Chuchu was in middle school or high school. So I'm going to show some recent results from my group, which kind of follow the intersection of these three areas. So what I'm going to show today falls at the intersection between three seemingly different areas, and I'm going to go through each of them very quickly, just to emphasize. Still something's not okay. Just to emphasize some advantages and limitations of each of them, and try to understand why I want to be at the intersection. So in control theory, most of us here are familiar with control theory. We know how to deal with realistic dynamics. When I say realistic dynamics, I mean continuous space, continuous time, systems of differential equations, sometimes continuous space, discrete time, sometimes PDEs. And you see, I'm perfectly timed to that. Most of the times we're interested in a stabilizing system. We want to converge to some desired state and hopefully stay there. While doing that, sometimes we're interested in optimizing some costs, such as distance traveled or energy consumption. And I would say the limitations to having control theory is the lack of expressive specification languages. So as I just said, we usually want to go to some point and stay there. If we're more sophisticated, sometimes we talk about safety, we want to make sure to stay away from obstacles, but that's kind of about it. Formal methods, and again, some of us here have background in formal methods, we kind of address that limitation. We have expressive specification languages such as temporal logics. Very simple example in a toy robotics environment, say that you have a partitioned environment and some regions of there are of interest. You have, you're going to see there are recharge regions, there is a dangerous region, there is a gather region. The robot is the black disk. And you can easily formalize a rich specification like that. You can say, keep on collecting, keep on recharging, do this before you do that, never do that, and so on. And here I'm showing an exact translation of this English specification into a formula of a specific logic called LTL, linear temporal logic. Also in formal methods, we have, you know how to compose systems. So let's say that I have a system described by a state transition graph. Think of the robot moving in the partitioned environment. I can represent it as the motion on a graph. And then I have a specification like the one that I showed you before. Most of the time you can translate that to some sort of an automaton. And in formal methods, we know how to compose them together and produce larger graphs, and then a verification or a formal synthesis problem can translate to some sophisticated search on a graph. Most of the time, an automaton game, such as rubbing game or bookie games, if you guys are familiar with that. We also understand compositionality of system components. If you have two robots talking to each other and synchronizing through some common actions, you can define a notion of compositionality between the corresponding models. And the limitation, I would say, is the fact that in formal methods, at least in the traditional approach, we don't know how to deal with complicated dynamics like in control theory, but rather with just very simple state transition graphs. Think of writing the mathematical model for some computer program. You can have the states as the values of the program counter, and then you can sequentially go in the increasing the program counter and then having jumps and so on. And then finally, machine learning. I guess we all know, we all work in machine learning. We know how to deal with unknown dynamics, and we have data-driven approaches. It's the first time when I'm not doing perfectly here. Okay, perfect. So, so again, machine learning somehow magically produces very good results in many areas. I think the main challenges here are interpretability, correctness guarantees, safety guarantees, and so on. So then if I start looking at the pairwise intersection between these areas, in between control theory and formal methods, you can try to solve control problems for systems with realistic dynamics from rich temporal logic specifications. There's been a lot of work in this area. In my group, we're very interested in abstraction-based approaches where you take the state space of a dynamical system, then you cut it into pieces, produce a graph, like an abstraction graph, and then come up with an automaton that captures this specification, composing them and doing all sorts of things in the discrete world, right? And then coming back and having some formal guarantees in between. More recently, we kind of realized that these methods do not scale, so there's a lot of optimization-based approaches to solve these problems. More or less cutting the time into pieces and then assigning satisfaction at every time step, and mapping a control synthesis problem like this to a large optimization problem that somehow maybe translates to a MILP that can be solved quickly. Going from machine learning to control theory, I guess we're all familiar with reinforcement learning, so the environment is not known, but we apply action, we see outcomes, we measure rewards, and then try to learn the environment at the same time with developing a control policy. Also in between control theory and machine learning, coming from the control theory side, I guess adaptive control is the framework that we're most familiar with. In adaptive control, you have, so the system that I showed there has a known drift, the f of x was a drift. Then we have some control directions, which are in the columns of this matrix G, and that's the control. And in adaptive control, most of the time, people assume some uncertain parameters acting along some constant known directions, which are the columns of this matrix F. And the goal here again is to stabilize the system and to construct a feedback control strategy that depends on a measurement. So data is acquired over time, and also depends on an estimate of the parameter. And we also have to construct an estimator to hopefully converge to the true value of the parameter so that you can achieve convergence, even though the parameters are not known, but data is collected and the parameters are estimated. In between formal methods and machine learning, there's been some work on verification of neural networks. Say that you have some plant, and let's say you learn a control policy as a neural network. There are approaches out there trying to prove that those neural networks satisfy some safety properties or satisfy the specification. Temporal logic inference, that's something that we've been interested in, is literally just do machine learning, but infer classifiers that are interpretable. So when I say interpretable, I mean something that's, again, some sort of a temporal logic formula. This looks different than what I showed you before. This is actually a timed logic. It's called STL, signal temporal logic. So think of you, so the first project that we had on this was actually from Denso in Japan, which is a automotive company. So they were interested in a gas exhaust system of some sort, and they had measurements, and they tried to see whether they can look at those measurements and infer whether the system is functioning normally or not, right? So they would give us a lot of data over many time points, like thousands of time series, and then the question is, can you classify, and can you classify in a way that we understand what the problem is, right? So we showed that you can actually construct classifiers that look like this. And also there is a nice connection between this and this, because then let's say that I want to control some, let's say that I have an aircraft and I want to deploy it into some hostile environment, and my specification is going to be a temporal logic formula. And then before I do that, let's say that I observe the environment and I want to characterize it somehow. So I'm going to construct another temporal logic formula which captures my knowledge about the environment. And then these two formulas, I can compose them together into a synthesis problem, right? And I'm going to show an example like this later on. And also, towards the end of the talk, I'm going to talk about something called specification-guided reward shaping, which falls at the intersection between machine learning and formal methods. More or less, you take formulas of this type and you can quantify satisfaction. So if I want my robot to do something, I'm gonna formalize the task as a formula like that, and I can quantify how well I'm satisfying that formula, and then I'm going to use that as a reward during the exploration process in reinforcement learning. So the three applications that I'm going to show, as I promised, are going to be at the intersection in here. First, I'm going to talk about some autonomous driving application that actually Wei, sitting right there, did, and then two manipulation projects. So here's the structure for the rest of the talk. First, I'm going to focus on systems with perfectly known dynamics, and then I'm going to gradually relax this assumption. So first, I'm going to assume that I have some partially known parameters. I'm going to be in the framework of traditional adaptive control. And then I'm going to assume that I don't even know the dynamics, but I have some knowledge of the dynamics. And then all the way to the bottom is like a fully blown machine learning approach in which I assume that I don't know the model at all. And the question is, again, what kind of safety guarantees can we have when we solve control problems under these assumptions? All right, so I'm going to start with the automotive example. There's Wei sitting right there. He was in my group. Actually, he was not in my group. He was at Motional, and we both happened to be there. This is a autonomous driving company that's here in Boston. And here's the problem that we looked at, right? So, which I guess most of you are familiar with. I have the autonomous car is called Ego. The goal here is to deploy this car from a specification which looks kind of like this. So I want to follow a path. I want to stay along a path, and this path would come from a group in Motional which was called motion planning. So they would give us a sequence of waypoints, and they would require the Ego to stay as close as possible to that path. At the same time, we had a bunch of physical limitations for the vehicle, such as steering angle, vehicle speed, steering control, jerk. These are all like bounded. And we wanted to minimize energy consumption. And I think the most interesting part is that we wanted to have some sort of a global minimization of violation of traffic rules. Because realistically, you cannot satisfy all the traffic rules. Like if you look at this ones, for example, I definitely want to stay away from pedestrians when I deploy an autonomous car. And I want to have clearance with respect to parked vehicles, moving vehicles. And then I want to stay in the driving area, I want to stay on the road, hopefully I want to stay in my lane, and so on. And I also maybe satisfy some speed limits. But so in a situation like this, if the Ego has to go and avoid some parked vehicles in here, there's no way it can stay in its lane, so it has to violate some of the rules. So it kind of makes sense when we present these rules to have them prioritized. And the priorities here go up in this direction. So the highest priority is to have clearance with respect to pedestrians, and then clearance with respect to other vehicles. And then what I care about the least is minimum speed limit. So can we generate control laws that kind of minimize the violation of these rules globally? If you look at those specs, they're all of the type, like for all times, make sure you don't do something bad. So I'm going to call those safety specifications. And as I said, a path following here is actually going from one waypoint to another. So it's like converging to a sequence of points. So I'm going to call that convergence. So very briefly, a few words about convergence and then safety. And then let's see how I can put them together in an optimal control problem. So for convergence, there is a well-known concept called control-Lyapunov function. Long story short here, we're going to focus on systems which have that particular structure. So there is a drift, there are some controls directions in the columns of the matrix G, and then there is a control. And very important here that we have tight bounds on the control. And the goal is to have a control strategy that stabilizes the system to the origin. And obviously that origin can be then translated. And even stronger here, we require global exponential convergence. And it turns out that if you can construct a Lyapunov-like function V that satisfies some constraints, I can come up with a very simple sufficient condition for stabilization. So if I can find a control U that satisfies the control bounds and this inequality for all x's, then the origin is guaranteed to be globally exponentially stable. So again, assume that we have this function somehow, miraculously have this function, then I just want you to pay attention to this inequality and note that if I keep the state x constant, then that inequality is actually affine in U, or whatever, linear in U. Good, so it's a linear inequality in U, right there, if x is constant. Something very similar and actually inspired from this for safety. So we formulate safety as forward invariance of some set, C, and I'm also going to assume that this set can be described using a differentiable function B. Same type of system, same type of control constraints, and again, you can come up with a sufficient condition for safety, which says that if I can find a control U such that this inequality is satisfied for all x's, then C is guaranteed to be forward invariant, which means your system is safe. Any questions so far? Try to answer the questions when the screen is blank, please, so we can use the time properly. So, and again, here you can note that if the state x is constant, then this is actually a linear inequality in U. Okay, so what I'm gonna step back to my original motivational problem, right? So what I want to do here, I want to control this system. I have control bounds. I want to minimize, let's say, some quadratic in U, and I want to satisfy safety and convergence. Given what I showed you before, if I can somehow come up with the CLF function, the control Lyapunov function V, and the control baryon function B, then this problem can be mapped to a nonlinear optimization problem. Right? So this is my cost, happens to be quadratic. These are the dynamics, which is a constraint for controls, and this is for convergence, and this is for safety. Right? So in general, this is obviously ugly on nonlinear optimization. The question is, and you know, if I have a very strong optimizer, I can hopefully maybe solve this problem. I'm going to solve it all the way globally from 0 to t and find optimal control, optimal sequence of states and everything. But again, that's a hard problem. So what people did, they came up with an approach which makes this computationally very attractive, but also, you know, compromising on both safety and convergence. So rather than, again, just solving this exactly from beginning to the end, think of discretizing the time, cutting into, let's say, uniform, many pieces, and then solve the problem in each of these time intervals. So what we do here, basically, we keep the state constant at the beginning of the time interval. And then if the state is constant, then you can notice that these two inequalities are actually linear in X. I'm also going to assume now that the state U is polyhedral. So that's another set of linear constraints in U. So linear, and this is a quadratic cost. Right? So so at every time step in here, I'm going to solve a QP, which can be solved very fast. I'm going to find the control U. I'm going to apply it to the dynamics. I'm going to integrate forward in time. Right, so it's a piecewise constant control. The control is going to be kept constant during this time. And then I'm going to end up at a new state, and then I'm going to reiterate the process. Right? So think of this, it's like a very aggressive, myopic approach based on discretization. And you know, it's shown that it worked, that it was applied to many robotic systems. So what we did, and actually, you know, Wei being there, you know, what Wei did, you know, when he was in my group, we started looking at, he was very interested in this problem. He said, I want to work on this problem. I said, no, but he said, yes, and we ended up working on this. And so there were some limitations of this approach. Like, first of all, in the traditional approach, which I'm illustrating here through a very simple example, it doesn't even work for some very simple systems because some of the terms in the sufficient condition can just vanish. In exactly the same way that you cannot sometimes solve an input-output linearization problem because some of those Lie derivatives vanish too because of some weird connection between the geometry of your dynamics and the geometry of your constraint. And that's very easy to see there. So what I'm showing there, it's a very simple automatic cruise control. So this is ego moving on a line, so a one-dimensional system, actually a second-order one-dimensional system. And then there is a preceding vehicle, and the safety here just requires a minimum distance in between the two vehicles. Right, so obviously the safety constraint is going to be that this is positive, right? So the distance larger than delta. If you just plug it in blindly into the equation that I showed you before, one of those, by the way, these are LIDS derivatives, and I assume you guys know what they mean, right? So I have some scalar quantity. I want to see how it changes along a vector field. Then I'm going to compute the dot product between that vector field and the gradient of the scalar quantity. So that's the LIDS derivative. So in that case, it happens that this term actually vanishes, so there is no control in your inequality, so this inequality is useless. So what Wei did, basically, he came up with this idea of actually using what's called relative degree, which means the number of times you have to differentiate the function before you can actually see the control, to iteratively define a sequence of functions. So rather than just having one CBF, you actually have m CBF type functions, where m is the relative degree. So this would be the first one, which is your original barrier function, and then this one defined iteratively. And then you can come up with the version of the sufficient condition that you saw before, which is a bit more general, a little bit more restrictive too. So you can enforce the forward invariance of intersection of sets, where each of the set is given by the corresponding CBF function from here, if you satisfy this constraint. This constraint looks a bit more complicated. There are some terms here which we're not showing, but what's important to note is that, again, as before, if I keep the state x constant, that this gives me a linear inequality in U. So that QP approach, we want to have that QP approach from before so we can compute things fast, so that works. Another more interesting limitation of those approaches is the fact that they can become easily infeasible, right? So if I were to solve the original optimization problem, basically you look all the way to the end, so you solve globally, so you have some sort of a notion of completeness in that optimization problem. In this one, you become computationally way more efficient, but you're myopic. So it's very possible that at some time point, I solve the QP, I find the control, I apply it for some period of time, I literally close my eyes because I don't know what's going to happen in the meantime. And when I get to the next time point, I'll look at the state. I plug it into the constraint of the next QP, and that can be empty, right? So my QP can become infeasible. How can you prevent that from happening, right? And those of you familiar with MPC, which is a little bit less myopic than this, you look over many time horizons in the front, this can happen too. And there's terminal constraints in there and all sorts of tricks that you can play. So what can you do here? One thing that you can do is exploit the structure of the modern of the iterative definition of the control barrier functions and introduce some more constraints, some more control points in there. Like, for example, all we care about is that this whole thing here is what's called the class K function, and if you insert some extra variables in here and ensure that they stay a class K function, and in order to enforce that, you're defining some extra auxiliary dynamics and control that to enforce your constraint, then you can actually make the problem way more feasible. Right? So it's literally by just inserting more variables into the problem and constructing dynamics that enforce the conditions that these terms have to satisfy. Second time it happened. It's an interesting way to give a talk. You can try to also learn infeasibility, right? So what Wei did here, he said, okay, think of a robotics problem and you want to move in a very cluttered environment, like many obstacles everywhere. And infeasibility most likely is going to happen when you get very close to obstacles, right? Because you're moving, you don't know an obstacle is close, and you apply some control, you end up close to the obstacle, that's when you violate that safety constraint. So one way to deal with this intuitively would be to sample very finely around the obstacles, generate a bunch of points in the state space, take those points, plug them into the constraints of your optimization problem and see if it's feasible or not. So if it's feasible, label it with, I always think of Wei when I show this, because he labeled the feasible ones with red and the infeasible ones with green, which to me doesn't make much sense, but too much work for me to change that, so I'm still using them like that. and then classify them, right? So hopefully I can build a classifier that's given by some differentiable functions, which is going to separate feasible from infeasible. And then I'm going to use this as an extra constraint in my optimization problem, right? And then it's kind of unintuitive here because I'm adding constraints to make a problem feasible. But if you think about it, it's the extra constraints are going to guide me from making decisions to become infeasible, right? So if I'm close to an obstacle, and if I don't have any constraint, I might end up too close, and then I'm becoming infeasible. If I have an extra constraint that's going to tell me to steer away, that is an extra constraint, but it's going to help me actually stay feasible. And you can see in there, and actually we also came up with some nice symmetries into the problem. Like for example, if you can if you can construct constraints for some obstacles of a certain shape, then they can be translated and rotated around. I cannot run movies. Oh, here I'm still seeing my original slide. It's not good. All right, let me try to do this again. Any questions so far? Yeah?
Yeah, for the optimization part, is it possible to use snap variables to make the optimization feasible? I think it's a common trick to
Yeah. And we do that all the time. Like for example, for convergence, we always use slack variables, right? Because going precisely to a point that I want to go is not that important, so we always slack those. And I think I had something in the slides, I just forgot to say anything about it, but okay, I don't think I have any control over my computer anymore. I can use the Blackboard. It's the next step, right? So you use slack, right? So you see like at the top, the inequality with V, make them small equal than delta, put the delta squared in the cost, so you slack it. But for safety critical, you don't want to do that, right? Because it's if I'm allowing to bump into an obstacle, that's not such a good idea. If I'm just allowing not to converge precisely.
But usually, if you use a really large penalty
to
the objective function, and if the system can't find the feasible solution, you will find it, right?
You could. You can play with the penalties. By the way, wait's not even paying attention. If you want to participate and maybe provide better answers, please do that.
Yeah, I think you can have snack variable as basically a soft constraint, no matter how much penalty you put on the decision. So it's always a soft constraint. It's still possible to violate it. So that's why I think we don't put snack variable for safety constraint.
Okay. If you have an upper bound on the optimal advanced multiplier stuff, then that gives like a lower bound for how large the penalty should be.
I guess in the case of this new constraint that you add, it's not, you're using it to mold the behavior of your...
The new constraint here, yeah. Mm-hmm.
Yeah, right. So I guess in that case, a soft constraint could still mold the behavior in the same way, but you would ultimately have a hard constraint that might cause you to be infeasible, right?
Yeah. Other questions?
Another question.
Yeah, go ahead.
So even
No, you can ask the question later. Let's use this quickly. Okay, cool. So another limitation here, I would say that the methods that use this type of QP approach are based on the fact that we know the dynamics very precisely. Right, and again, if you come from control theory, the easiest way in which you can insert some, unknown, some uncertainty to your system would be like follow the adaptive control approach, in which you're allowed to have some unknown parameters acting along some known control directions. What was the question? Sorry, trying to.
Even when you have the classifier as a constraint, then you cannot guarantee that you can satisfy that classifier constraint.
Yeah.
Sometimes, right?
Yeah. Well, it's all, there is no guarantees in here. Once you start chopping things into pieces and slacking, and you just use your intuition and hope for the best, all right? Okay, so let's assume now we're under this scenario. The question is, can I extend everything? Can I still come up with something that is going to ensure safety, it's going to ensure convergence, and it can be reduced to solving QPs? And the answer is yes, with a lot of technical details which I'm going to skip. But I just want to remind you that this is what people do in adaptive control, right? So I don't know my parameters, but I can use the dynamics to enforce a bunch of constraints on the unknown parameters, right? So what I'm going to do, I'm just going to take some terms from one side to another, and I'm going to, at each time step, I'm going to have a linear constraint, whatever, set of linear constraints on the parameters, right? So you know f, you know g. Again, the state you measure. You might even measure the derivative at some point or estimate it from different time points. So basically, this is something that's known at time t. This is something that's known at time t. So at every time t, you're going to get some information about your state, right? And the easiest thing you can do is just use some sort of a least square approximation, do some line fitting to actually get some values for theta. So it turns out that you can actually do this kind of stuff, and you can come up with formal proofs that you can extend that QP algorithm from what I showed you before to something like this. Right, so in addition to what you had before, you're going to have some parameter estimates. Right, so at every time step you have to estimate your parameters. It turns out, if you look at technical details, there's something kind of unintuitive happening in there, in the sense that we have to maintain two sets of estimates for the parameters, one for convergence, one for safety. You can formally prove that they're both eventually going to converge to the true value of the parameters, but you literally have to integrate two different types of dynamics in order to ensure a safety and convergence, yes. Also, something that's not very intuitive in here, but if you look at the details, you actually have to have even an extra set of differential equations that you have to integrate at every time step, which provides an upper bound for something that you use in the safety part. But again, what I want you to note is that everything is exactly the same as before, it's just computationally a bit more expensive. In the sense that at every time step, so here at time 0, I'm going to start with the initial value for x, initial value for estimate for this guy, initial value for the estimate for this guy, initial value for this upper bound. So 4 kind of state variables, and then again, chop everything into pieces, and everything works exactly as before, and you have the guarantees. And I think the most important result is that the two parameter estimates actually both converge to the same value, which is the true value of the parameters. Which in adaptive control, if you guys are familiar with that, it's kind of a hard problem. Sometimes people can come up with proof that the system converges, but they don't have the guarantee that the parameters go to the true value. And again, there is a way you have to be sure that you need a computer with some memory. You have to have a stack of points. Literally, you have to stack all the measurements that you had from time 0 up to the current time step to form those. You might recognize here, this obviously comes from some sort of a least square optimization. That's what we're doing in there. And then they just add some extra terms to ensure convergence. Okay, and then you can make this a bit more sophisticated. Remember, we're talking about specifications given as temporal logics in here. And you can do that. What I'm showing at the top there is an LTL formula, which basically says that you want to enforce infinitely many visits to some region O1 and infinitely many visits to some other region O2, and always stay away from this. What you do, you come up with an automaton which accepts all the possible strings over those symbols that satisfy the formula. This happens to be, it's like an FSA, but it's actually a Bookie automaton because time is infinite. Again, I don't want to spend time here, but the question is, how do you enforce the acceptance condition of the automaton when you control this system? And you can use CLFs, because CLFs they're taking you somewhere. So you can show that you can use CLFs to go from one state to another, and you can use CBFs to make sure you don't step into trap states where you would violate the formula. It would not satisfy the acceptance condition of the automaton. There is a lot of conservatism in there, but there's proofs of correctness that you can do this properly. Obviously, this has way more complicated semantics, has some guards, because you need to know when you have to switch from one to another, but you can write it as you might be familiar with the hybrid automata, right? So there is some guards in here and some resets, but you can work this out with a lot of conservatism. In the sense that if you find the solution, it's correct, but you're not guaranteed to find it. Okay, so back to the original problem that I showed you. Remember, I want to control my ego to follow a set of waypoints in the middle of the lane, constraints for the state and for the control, minimize energy, and somehow minimize violation of a prioritized set of rules. Right? So as I said before, so I'm going to use CBFs for the enforcement of those. I'm going to use CLFs for following the waypoints. The question is, how do I take care of the priorities, right? So think of, I have like, 10 rules, and I want to satisfy them all. So I can have a very greedy approach in which I can formulate an optimization problem in which I'm going to first require the satisfaction of all the rules. And by the way, going back to the question on slacking, we always slack convergence, right? I want to make sure that doesn't give us any problems with the feasibility. And then if I don't end up with a solution, and again, I'm going to enforce all the safety constraints, all the rules, I'm going to enforce them precisely. I'm not going to slack any of them. If I end up with a solution, then I'm happy that's going to be a solution. I somehow managed to control my vehicle to satisfy all the rules. If I don't end up with a solution, the simplest and most intuitive thing would be to start relaxing from the bottom, right? Like at the bottom there, I had the minimum speed limit. Well, that's not that important. I can move a bit faster, and maybe if I violate that, I can still find a satisfying solution. So that's kind of it. And then you just keep on relaxing until hopefully you can get something that works. And hopefully you don't have to relax the, running over pedestrians. Hopefully that's going to be satisfied. Here are some examples. Here the goal is to, here's a scenario. So you have an active vehicle, this vehicle moves this way, and two parked vehicles, pedestrian here. It turns out that you cannot satisfy them all, but apparently you can come up with a solution that only violates minimum speed limit. And to understand that, maybe I should run this movie to see that in order to ensure clearance, what we have is a box around the ego. And then, so this box gives you clearance, right? And that box actually, the size of the box is a linear function. It depends on the speed. So the faster you move, the bigger the box is, so you can, make sure pedestrians are safe. So what happens in there, you actually have to slow down a lot to ensure the pedestrians are safe. So that's why you have to violate the minimum speed limit. Good, so this should make sense. More complicated examples, in this case, because of the geometry of the scenario in here, you actually have to violate both the stay in lane, which was kind of still a low priority rule, and the minimum speed limit. And again, this is done automatically, but it's a lot of computation. It's a large number of optimization problems solved in a loop. Okay. So I said I'm going to start relaxing the assumption that I know the dynamics of the system. So far we could only deal with some unknown parameters in the dynamics. The dynamics were assumed in a certain form with drift plus control directions. So now I'm going to look at this example and I'm going to relax this assumption. So what I'm showing here, this is actually simulation. It's a Baxter, which has, I think, 45 degrees of freedom or something like this. And it's a very simple pick and drop application. So it's supposed to pick up something, drop it there, and I'm give the specification again in English, and I'm color coding it here to show that there are some Boolean connectors there, such as AND, and also some time constraints like deadlines in this case. So what do we do here? I'm going to show this and I'm going to talk over it. I think time-wise I want to try to wrap it up. So the only assumption that we make in here is that the dynamics are of this form, which, if you're familiar with kinematics and dynamics, most of the mechanical systems that we have out there, they satisfy this assumption, right? So, and Baxter does. Every manipulator arm actually you can write it in this form with the drift, control direction, and then control enter in here like this. So we assume that the dynamics are of this form, but we don't know what the dynamics are, right? Writing down the 45-dimensional system and using it for control is a bit unrealistic here. So what we did, we first of all ran the system a little bit, so literally just moved the manipulator around by just applying some controls. to get a little bit of data, to get some initial estimates for the drift and for the control directions. And to do that, basically what we do, again, this is the state that we're minimizing the distance between the state that we can measure and the estimate that we can get from the model, right? So by doing this, you can actually construct like a very simple neural networks for the drift and for the control direction. Once you have those, you're trying to find a policy for that preliminary model that you have. And for that, we solve another machine learning problem where what we're trying to do is to maximize satisfaction of my specification. So the specification in this case is a formula on a different logic than what I showed you before. This logic is timed. It's called STL. So what's nice about this logic is that you can, so first of all, their semantics is given over the timed executions. So think of, manipulator I'm moving around, it produces a motion, then I can check the satisfaction of the formula by this motion. Now what's nice about this logic is that it has quantitative semantics in the sense that I can come up with a number called robustness and denoted by rho in there, which shows me how well I satisfy. So what I'm going to do in here, I'm actually going to find a control policy by maximizing the degree of satisfaction. Good, so it's like a two-level machine learning process. First, I learn the model a little bit, and then for that model, I find a policy that maximizes satisfaction, check if I have convergence. If I don't, I'm going to keep on collecting data. I'm going to update the model, update the control policy. So there's nothing, spectacular in here, but what's interesting is that the procedure is extremely fast. So literally in I think 45 seconds, we're done, right? So literally just moved around for like 10 seconds, get f hat and g hat, then learn this. And by the way, this is an RNN. So this is an FNN, but this is an RNN because STL has memory. So you can show easily that, in order to be able to decide satisfaction of a formula in STL, you need to have some notion of history. So why not use a neural network that has history? And we actually showed before that RNNs perform much better than FNNs or CNNs. And I have some movies here again. I'm going to skip, but it shows that it actually learns very, very fast. Charles.
So on the last slide you had the box CDFs. What model are you using to evaluate your CDF?
Where? Here?
Are you using the learned model to evaluate the variance?
CBFs here are so safety means the distance from obstacles. So this CBF, the safety here is as good as the model is. So if the model is not good, then safety is not going to be good. Right? So we do the best that we can. And, that's another reason why we have this, but, remember, this is the kind of dynamics that we can use when we do CBFs, and we exploit the fact that the model is actually in that form. Good? Okay. All right, so it works fast. Do we have any proofs? There's no guarantees of anything here, but it just works. Another example. Okay, so I'm just going to show you like a more robotics, like a fully blown example in which we literally don't make any assumptions on the model. This is literally like the RL framework, right? So you characterize the environment by, discretizing into certain regions, and then you enumerate a set of actions, and then you apply actions, look at outcomes, try to learn the relationship, try to learn, transition probabilities between states in the environment and robot states, and also come up with a policy at the same time. So that's what we did in here, and it's there's two robots. One is a cook, that's Jaco, and one is that's we have a chef and a server. That's how we call them. So that's the chef who picks up hot dogs, put them on the grill. I'm not sure. Wait, were you in the lab when this happened? I don't remember. So wait, by the way, he's in CSAIL here in MIT, but he just nice and came to my talk. But he actually, So we even had ketchup and mustard initially, and that was not a good idea. Then the ketchup and the mustard then became just plastic bottles, which were empty. But so again, this guy cooks. This guy, when there is a request with the plate, then it's going to serve a hot dog if the hot dog is ready. So the main idea here is that you can come up with a very, very large set of rules written in English describing things that you want the system to do, and also some prior knowledge that you have about the system, right? Like Don't pick up a hot dog if you don't have a bun in your other hand so you can put it in there. Or don't put the hot dog on the grill if the grill is not hot already. These kinds of things. So these kinds of things, you can translate them into automata. So we have this type of automata, which we call them finite state predicate automata. And what's nice about this automata is that you can always quantify the progress towards satisfaction, because you can quantify satisfaction of the predicates, but also some sort of a distance towards final state, so you know how far you are from satisfaction. So then I guess you guess what we did in here. We used this measure to shape the reward during the RL process. And that's kind of it, right? So this, using the spec to shape your reward to make sure RL goes, in the direction that you want. The notion of compositionality, you can construct large databases, and Chuchu, maybe you can solve the problem of going from English to automata, right? Because you're working in this area. It would be nice to actually just talk to the system and give them 20 specifications and then automatically generate the automata, and then because they compose. That's what's nice about them, can compose them. So here's kind of the big picture here, right? So we have specifications and knowledge. We can do a little bit of, depending on the logic that you are in the shape of the predicates, you can, if you're in a decidable theory, you can do a little bit of a set over there and make sure they not contradict with each other, and if they're satisfiable, then you compose all this. You can have like a quite large finite state predicate automaton which captures knowledge and satisfaction, and then you can start doing RL. And then what I'm showing in here is that, and I was telling you before, you can try to enforce some safety in there. So once you have an RL action, you can try to adjust it a little bit to enforce safety, right? So think of you solve really a quadratic program. You want to minimize the distance between the control given by the RL and what would be a safe control, and then apply that to the system. So you enforce safety, but you can mess up a little bit with the convergence rate of the control policy if you do that. And you got nice experiments, and it's very, very robotics. So you can watch here. But so again, we did. What's nice about it is that we trained on like small portions of the task. Like Jacob did something for a little bit, and then you guys want me to run the movies? Let me try. Is it running? Yeah, it is running. Okay, so maybe I can I can take some questions while you guys look at this. So there was a lot of training, both in experiment and in simulation, and then experimental validation after learning. And this took time. It was not as fast as the one that I showed you before.
So the CBF is only for the end effector or for the entire?
End effector, only the workspace. We solve a very good question. So we're not working in 45 dimension with the CBF. We shouldn't, even calling it CBF is an overkill. I shouldn't do that. And let's say it's some sort of an adjustment at the end to ensure obstacle avoidance in the 3D workspace. Okay, so the people, way is right there. And actually, all these people, only one is in my lab and is graduating in 2 months. Yeah. No, Wei-Liang is actually going to Amazon, so he already has a job. And that's your friend Zach. And Shao was here too, yeah, right? He's in, where is Shao now? He's in Shanghai Jiaotong, yeah.
Okay.
Nice, thank you.